Continuing onward, I believe the next section deals with Hashmaps. Hashmaps. And I'm having my editor over here because we're definitely going to be doing something. All right. Storing keys with associated values in Hashmaps. The last of our common collection is the Hashmap. The type Hashmap KV stores a mapping of keys of type K to values of type T. It does this via a hashing function, which determines how it places these keys and values into memory. Many programming languages support this kind of data structure, but they often use a different name, such as hash, map, object, hash table, dictionary, or associative array, just to name a few. Hash maps are useful when you want to look up data not by using an index, as you can with vectors, but by using a key that can be of any type. For example, in a game, you could keep track of each team's score in a hash map in which each key is a team's name and the values are each team's score. Given a team name, you can retrieve its score. We'll go over the basic API of hash maps in this section, but many more goodies are hiding in the functions defined on Hashmap by the standard library. As always, check the standard library documentation for more information. Noted. The only thing I'm really curious about, because I'm not even sure if it's true, is that they said up here, where is it? A key can be of any type. I know in a lot of other languages, keys must be hashable, and there are some things that you just can't hash. But here it says everything can be a key. So, looking forward to seeing if that's true. All right, creating a new hash map. You can create an empty hash map with new and add elements with insert. In listing 8-20, we are keeping track of the scores of two teams whose names are blue and yellow. The blue team starts with 10 points and the yellow team starts with 50. Cheaters. Okay, let's write that in. And they used yellow, but I'm all about red and blue, so I'm gonna use red and blue. Standard library, collections, and then we're going to import Hashmap. Got it. And here we're going to say let mutable scores equal Hashmap new, and then we're inserting scores. So scores dot insert, and oh, they're key values, that's why. String from, we're gonna make you the blue team, and scores dot insert string from, and I'm gonna make you the red team. And I'm gonna say you start off with 20, because starting off with 50 is just to be curious. I'm pretty sure we can iterate over them, like for KV in scores. This I'm just guessing. I haven't actually done this before. And no, that does not look like it works. Do I have to make it a tuple? I do. For KV and scores, print line hopefully this works. K and V. So I would love to see this working. Cargo run. Alright, so what I'm doing here, hopefully this compiles and runs, is that we have created a hash map of scores. We have inserted a key of blue with the value of 10, key of red with the value of 20, and then we're trying to print these out. And it looks like we can print these out just by iterating over them. Blue team, red team. Cool. So you know that works. Note that we need to first use the hash map from the collections portion of the standard library. Of our 3 common collections, this one is the least often used, so it's not included in the features brought into scope automatically in the prelude. Hashmaps also have less support from the standard library. There's no built-in macro to construct them, for example. Just like vectors, hashmaps store their data on the heap. This hashmap has keys of type string and values of type I32. Like vectors, hashmaps are homogeneous. All of the keys must have the same type, and all of the values must have the same type. Okay, so what they're saying here is all the keys and all the values from here on onward have to have the type string for a key and type I32 for a value. They stay homogeneous, which means anything that's newly inserted has to conform to that structure, or that constraint, I should say. Another way of constructing a hashmap is by using the collect method on a vector of tuples, where each tuple consists of a key and its value. The collect method gathers data into a number of collection types, including hashmap. For example, if we had the team names and initial scores in 2 separate vectors, we could use the zip method to create a vector of tuples where blue is paired with 10 and so forth. Then we could use the collect method to turn that vector of tuples into a hashmap as shown in listing 821. They're not showing, oh no, they are showing the zip portion. Okay, so we have the teams, we have the vectors, 2 teams, initial scores, we zip them to make them into tuples, and then from the tuples we use the iter and make them into hashmaps. So we should still be able to use scores, but we're no longer inserting them this way. So let's get rid of that. Let teams equal vec macro, and then create these 2 strings from blue no from red initial, oh sorry, I forgot to let initial scores equal another vector 10 and 50, and with the flashiness let's create scores. Scores is going to be of type hashmap, and here it looks like we have these underscores, which probably means inherit or figure out what type they're going to be. Teams.iter, so teams, it has the vector of 2, and that is blue and red, and we're going to iter over them, and we're going to zip them with the initial scores iter. Alright, so that's just taking the blue and matching with this 10, red and matching with this 10, and returning that tuple, and that tuple is going to be turned into a hashmap. If we use the collect at the end of it, that's what I was not seeing. Alright, so that tuple, which is the return value of these things as they are now, we're going to call collect on that, and that should create our hashmap, and everything is the same. Well, bring the score down a little bit, they don't need 50 points. Now everything is the same. All right. The type annotation hashmap less than sign, underscore, comma, underscore, greater than sign is needed here because it's possible to collect in many different data structures, and Rust doesn't know which you want unless you specify. For the parameters for the key and value types, however, we use underscores, and Rust can infer the type that the hashmap contains based on the types of the data in the vectors. So yeah, they just underscore, tell the compiler to infer. they infer correctly. We need a type annotation because collect can be used on many different data structures, not just Hashmaps. So you can collect and change it into something else. So that has to be explicit so the compiler knows what you're trying to change it into. And moving on. Hashmaps and ownership. For types that implement the copy trait, like I32, the values are copied into the Hashmap. For own values, like string, the values will be moved and the Hashmap will be the owner of those values, as demonstrated in listing 822. Okay, so we have our Hashmap, imported it. We have a field name, favorite color, value, blue, and we're creating a Hashmap new, and then we're inserting field name and value. And then if we want, we can try to access field name or value, and we should get an error saying that it's been moved. I'm willing to test that out. Let field name equal string from, and they have favorite color. Yeah, favorite color is fine. Favorite color. Let field value equal string from purple. Purple is much better than blue. Oh, I'm missing a. Here we go. I'm missing an ending bracket. Let mutable map equal Hashmap new. I'm not sure if I saw that before. Hashmap question mark random state. I don't remember seeing that, but I believe that's correct. And then we can do map dot insert field name. Oh, and now at runtime, well, technically it's just being recompiled. No, this would be the editor runtime. They changed that to string. And now here, we can say field value, and that's going to change to string. Huh. That's kind of cool. And then if we want to, first let's print this out to make sure it exists. So for key and value, and what did we call it? We just called it map. Print, get rid of this T. Key and value. Value. And we have that. So now if we try to print field name, because it's been moved, we should get an error. Let me get rid of this. And cannot compile. Says it, so borrow of moved value. So that is the correct error. It should be moved. This whole doesn't have copy trait. Oh, it doesn't have the copy trait. Yeah, that's what they were saying. So it has been moved. This is the correct error. Cool. Everything seems to be in order. We aren't able to use the variables field name and field value after they've been moved into the Hashmap with the call to insert. If we insert references to values into the Hashmap, the values won't be moved into the Hashmap. The values that the references point to must be valid for at least as long as the Hashmap is valid. We'll talk more about these issues in validating references with lifetimes in Chapter 10. Chapter 10 used to be really far away, not so much anymore. And they're saying, what they're saying here is that if you, so in this example, we had a string that was placed in the heap, right? And then we set that value in, we put that value into our Hashmap. Our Hashmap then took ownership of those strings, and thus field name and field value were moved. They were moved into our map. However, another option is if we put in pointers to values into our Hashmap. So if we did that, then our Hashmap does not take ownership of it because they're just pointers to the actual values. But given that these pointers to these values live in our Hashmap and these values live someplace else, there has to be sort of a lifetime check, because if these values go out of get deallocated before, and if these values get deallocated and we try to use our Hashmap, then we have an issue because those pointers now point to memory that has already been freed up. And they correct that issue seemingly with validating references and with lifetimes. I'm going to say that again because that was really jumbled. So the issue that they bring up here is a different example than this one. In this one, we have a memory, we have a variable that is placed on the heap, our string, that is owned by field name, and field value has its own that it owns. When you pass these into the map now takes ownership, the Hashmap now takes ownership of them. However, there is also the other option where you can pass in references to these variables. And if you did that, the map does not take ownership of the references. However, you now have to guarantee that these references will exist as long as this map does. Because if they were to not exist, if they were to stop existing prior to the map and then you try to access them, you are now trying to access memory that has already been freed. That is an error. And seemingly Rust corrects this with lifetimes, which we will learn about in chapter 10. Accessing values in a Hashmap. We can get a value out of the Hashmap by providing its key to the get method, as shown in listing 8-23. Alright, so now they're going to show us for the first time how to get the value out of it. I've been iterating over it just so I can print it. They probably go over that a little bit later, but let's do this. Alright, so let's go over this example real quick. I'll just erase this and then write what they have for parity. So they started off with a new map, new Hashmap. They're called Hashmaps in this language. So scores equals Hashmap new, and they inserted two scores. Scores dot insert string from. They made this team blue, and they gave it a score of 10, value of 10. Scores that insert string from, put that back there, and I call this team red, give you 20, and then they created a variable for the team name, an immutable variable that we're going to use to access the Hashmap. So we created this string, and they made the value of it blue, which is the same as the team name. And now we're saying let score, which really like the blue team score, I'm gonna call it blue score, equal scores dot get team name. Oh, this is a pointer. And then we can just print that out, make sure we have it. Blue score. And hopefully this works. Could not compile. And let's see what the error was. Oh, blue score is an option. That's probably what they're going to tell us to do next. I see. That makes sense. So get is going to be safe, and since this is an option, it can be sum with a value in it or none. In this case, it's sum with the value of 10. Here score will have the value that's associated with the blue team, and the result will be sum pointer 10. The result is wrapped in sum because get returns an option. If there's no value for the key in the Hashmap, get will return none. The program will need to handle the option in one of the ways covered in chapter 6. And one of the ways covered in chapter 6. Okay. Let's see if I remember how to do that. I believe that was match team name, and if it's sum, do I put the type? I do not remember. And I'm being bit by a kitten. Biting my feet. Biting my feet. You want to stay in here or do you want to get out, huh? Sum print. Oh, this is the name of the variable. I was spazzing earlier. So let's just call this score. Print score comma, and if it is none, print no score. And see if that works. Expected struck string. Wait, what? What happened to? Oh, I'm spazzing. What happened to my get? Score. Blue score. Equal scores that get pointer to team name, and then you are going to be blue score. So that took me a while to write, but now I have it. Cool. Just a quick overview. So we have the team, string blue, team name. We're going to use this name, the string, to get our value out of the map, which we do here. Let blue score equal scores.get team name, which is blue. And then since it's an option, if you want to access it, we can use the match, which we learned in chapter 6, where we can write something along the lines of sum, match, blue score, sum, score, which is going to take the value that's in the sum if it exists, and then we can use it. Or we can have none option, which is the second part of the option enum. It has two options, the sum and none. If there is none, we print there's no score. And what we have here is, after we ran this, score 10, because 10 is the value of blue. And now continuing onward, we can iterate over each key value pair in the Hashmap in a similar manner as we do with vectors using a for loop. And I've been doing this the entire video, so I'm going to skip over that. And we'll print out the information. Yep. Updating a Hashmap. Although the number of keys and values is growable, each key can only have one value associated with it at a time. When you want to change the data in a Hashmap, you have to decide how to handle the case when a key already has a value assigned. You could replace the old value with the new value, completely disregarding the old value. You could keep the old value and ignore the new value, only adding the new value if the key doesn't already have a value. Or you could combine the old value and the new value. Let's look at how to do each of these. Oh, that's kind of interesting. So we went over the 3 cases here. You could replace the old value with the new value, completely disregarding the old value, case 1. You could keep the old value and ignore the new value, case 2. Or you could combine the old value and the new value, which, given the rules for Hashmaps, those values have to be the same type. So yeah, case 3. If we want to overwriting a value. If we insert a key and a value into a Hashmap and then insert the same key with a different value, the value associated with that key will be replaced. Even though the code in listing 8-24 calls insert twice, the Hashmap will only contain one key value pair because we're inserting the value for the blue team's key both times. So what they're saying here, I'm not gonna write this one. Ooh, wait, I will write this one out. They're showing us something new here. So you can print out scores with the debug functionality. That's good to know. Team red, blue. I guess I can start from about here. Right? So we have immutable scores. We have blue 10, and then we change this to blue to match theirs, right? And we make that 25. Even when you insert blue score twice, you can't get up to 50. That's mean. And then we can print out the map, the Hashmap, using the debug syntax. Scores. All right. And we see that we only have one key and one value because we overrode the initial value for blue, which was 10. And we also see that we can print it out. The code will print blue 25. The original value of 10 has been overwritten. Second case, only insert a value if the key has no value. It's common to check whether a particular key has a value, and if it doesn't, insert a value for it. Hashmaps have a special API for this called entry that takes the key you want to check as a parameter. The return value of the entry method is an enum called entry that represents a value that might or might not exist. Let's say we want to check whether the key for the yellow team has a value associated with it. If it doesn't, we want to insert the value 50, and the same for the blue team. Using the entry API, the code will look like below here. So we have the Hashmap like we have for all of them. We created a Hashmap. We added blue team of 10. I guess they lose everything. And now we're using the entry. So according to what they said, scores at entry, we put the first parameter here, which is going to be the key that we're checking for. From yellow does not exist in our Hashmap so far. So when we do this, we should insert 50. And then if we try to do the same thing with blue, nothing should happen. Entry. Blue that or insert 50, and this is already printing out. So now we get that yellow has 50 points and blue has 10 points. Poor blue. The _insert method on entry is defined to return a mutable reference to the value for the corresponding entry key if that key exists, and if not, insert the parameter as the new value for this key and returns a mutable reference to the new value. This technique is much cleaner than writing the logic ourselves, and in addition plays more nicely with the borrow checker. I'm being bitten by a kitten again. Running the code and listing 8-25 will print yellow 50, blue 10. The first call to entry will insert the key for the yellow team with the value 50 because the yellow team doesn't have a value already. The second call entry will not change the Hashmap because the blue team already has value 10. Updating a value based on the old value. Another common use case for Hashmaps is to look up a key's value and then update it based on the old value. For instance, in 8-26, which we're about to look at, shows code that counts how many times each word appears in some text. We use a Hashmap with the words as keys and increment the value to keep track of how many times we've seen the word. If it's the first time we've seen a word, we'll insert the 0 value, or value 0. So here we have a word count program, seemingly. We have our Hashmap. We have the text, hello world, wonderful world. We have a mutable map. And then for word in text that's split by white space, so 1, 2, 3, 4 words, we're going to let the count equal map.entry word or insert 0. And, I see. So this is where we have the return value, which is going to be a reference to the value that's within the map. And then we can add to it. If it's not there, it will be placed in using the entry feature, entry method, as 0. And then we add 1 to that, which means we'll see it once. Alright, so I'm going to write this out after I get this kitten down. Alright, let me write this out real quick. Yeah, I'll just erase all of that. Let text equal, I'm gonna copy this. I don't feel like writing that entire sentence. Plus I might misspell something. Let mutable map equal Hashmap new. And for word in text dot split white space, let count equal map.entry, and we're going to search for the word within the Hashmap or insert 0. And then we're going to take these reference to count and add 1 to it. And now we can print the map. I did call it map, right? And I have an error. Invalid expression on the left side. Interesting. Did I forget semicolon? Could that have been it? And I forgot a semicolon. Cool. So we have hello 1, wonderful world, wonderful 1, world 2. We have it in a different order, which probably means that we cannot trust the order of Hashmaps, thus we shouldn't rely on them. The or insert method actually returned a mutable reference, mutable v, to the value for this key. Here we stored that mutable reference in the count variable, so in order to assign to that value we must first dereference count using the ASCII star. The mutable reference goes out of scope at the end of the for loop, so all of these changes are safe and allowed by the borrowing rules. Makes sense? Hashing functions. By default, Hashmap uses cryptographically strong hashing functions that can provide resistance to denial of service attacks. This is not the fastest hashing algorithm available, but the trade-off for better security that comes with the drop in performance is worth it. If you're If you profile your code and find that the default hash function is too slow for your purposes, you can switch to another function by specifying a different hasher. A hasher is a type that implements the build hasher trait. We'll talk about traits and how to implement them in Chapter 10. You don't necessarily have to implement your own hasher from scratch. Crate.io, which we've clicked on before, has libraries shared by other Rust users that provide hashers implementing many common hashing algorithms. And I'm guessing this is a PDF to the hash they use here. Oh, they actually give us the link to the white paper describing the hash. That's nice. Now down to the summary. Summary. Vector, strings, and hashmaps will provide a large amount of functionality necessary in programs when you need to store, access, and modify data. Here are some exercises you should now be equipped to solve. Oh, they gave us homework. Given a list of integers, use a vector and return the mean, the average value, medium, when sorted, the value in the middle position, and mode, the value that occurs most often. A hashmap will be helpful here of the list. So just to reread that, because they had a lot of parentheses and whatnot. Given a list of integers, use a vector and return the mean, medium, and mode of the list. And in the parentheses, they have the help, which is what I read out the first time. Second one, convert strings to Pig Latin. The first consonant of each word is moved to the end of the word, and ay is added, so first becomes ersve. Words that start with a value have hey added to the end instead. Apple becomes apple hey. Keep in mind the details about UTF-8 encoding. That sounds interesting. Using a hashmap and vectors, create a text interface to allow a user to add employee names to a department in a company. For example, add Sally to engineering or add Amir to sales. Then let the user retrieve a list of all people in a department or all people in the company by department, sorted alphabetically. Okay. The standard library API documentation describes methods that vectors, strings, and hashmaps have that will be helpful for these exercises. We're getting into more complex programs in which operations can fail, so it's a perfect time to discuss error handling. We'll do that next. All right, I guess next I'll have to do videos and solve these different homework assignments, problems 1, 2, and 3. Till then, I hope this was entertaining, hope this was useful. Peace.